What is the main research question addressed in the paper?
The main research question addressed in the paper is how learning new factual knowledge through fine-tuning impacts the model's tendency to hallucinate with respect to its pre-existing knowledge. The study aims to understand how large language models integrate new facts outside of their pre-existing knowledge during the fine-tuning process. Specifically, the paper investigates whether exposure to new knowledge during fine-tuning may lead the model to generate factually incorrect responses, known as hallucinations, as it tries to adapt to the new information. The research delves into how fine-tuning examples categorized as unknown affect the model's performance and tendency to hallucinate compared to examples categorized as known. The study also explores the training dynamics of large language models when exposed to new factual knowledge, and how this impacts their utilization of pre-existing knowledge.
How is the slick hierarchy of knowledge categories derived and utilized in the study?
The slick hierarchy of knowledge categories is derived and utilized in the study by first categorizing examples into mathed-known and mathed-unknown types based on whether the model knows the answer to a given question. The mathed-known examples are further divided into three categories: mathed-highly known, mathed-maybe known, and mathed-weakly known. The categorization is based on the model's consistency in predicting the correct answer when prompted with a question. Mathed-highly known examples are those where the model always predicts the correct answer. Mathed-maybe known examples are where the model sometimes predicts the correct answer, and mathed-weakly known examples are where the model never predicts the correct answer. This hierarchy is utilized to assess the impact of different knowledge types on the model's performance during fine-tuning. The study shows that learning from mathed-unknown examples is correlated with a higher tendency for the model to hallucinate, while learning from mathed-known examples leads to better utilization of pre-existing knowledge. The analysis of the training dynamics also reveals that the model fits mathed-unknown examples substantially slower than mathed-known examples, indicating the struggle of LLMs to integrate new factual knowledge.
Can you explain the impact of fine-tuning examples from each knowledge category on test performance according to the paper?
Fine-tuning examples from each knowledge category have a significant impact on test performance according to the paper. The study found that fine-tuning on mathed-highly known examples did not yield the best results overall, despite excelling on mathed-highly known test examples. On the other hand, fine-tuning on mathed-maybe known examples resulted in the best overall performance. Specifically, D_mathed-maybe known enhanced the model's performance on mathed-maybe known examples while maintaining high performance on mathed-highly known examples. This indicates that mathed-maybe known fine-tuning examples are essential for the model to handle such examples correctly during inference. Additionally, the study showed that fine-tuning on mathed-weakly known examples, though to a lesser degree, also increased the risk of overfitting and led to a decrease in performance, especially on mathed-highly known and mathed-maybe known examples. The results demonstrated that the composition of fine-tuning examples significantly influences the extent to which large language models, LLMs, effectively utilize their pre-existing knowledge, with mathed-maybe known examples playing a crucial role in enhancing performance across different knowledge categories.
How does the training dynamics differ between fitting known and unknown fine-tuning examples?
The training dynamics differ between fitting known and unknown fine-tuning examples in that LLMs fit unknown examples substantially slower than known examples. This is evidenced by the fact that during the early stopping phase, LLMs reach peak performance on the development set by fitting the majority of known examples, but only a small fraction of unknown examples. This slower fitting rate for unknown examples suggests that LLMs struggle to acquire new factual knowledge through fine-tuning, instead focusing on exposing their pre-existing knowledge using the known examples. Additionally, the study shows that the negative effect of unknown examples on performance is mostly observed in later training stages, indicating that early stopping can empirically avoid the negative impact of unknown examples as a form of overfitting. Overall, the analysis of training dynamics reveals that LLMs have difficulty integrating new factual knowledge present in unknown fine-tuning examples, leading to a slower fitting process compared to known examples.
What practical implications are discussed in the paper regarding the use of supervised fine-tuning on LLMs knowledge?
The practical implications discussed in the paper regarding the use of supervised fine-tuning on LLMs knowledge include the risk associated with acquiring new knowledge through fine-tuning, as it is correlated with hallucinations concerning pre-existing knowledge. The study found that LLMs struggle to integrate new factual knowledge introduced through fine-tuning, leading to potential hallucinations. The paper suggests that early stopping can help mitigate the risk of hallucinations caused by fitting unknown examples, as they primarily emerge as a form of overfitting in later training stages. Additionally, filtering out unknown fine-tuning examples can reduce the risk of overfitting without sacrificing performance. The study also raises the question of whether relabeling unknown examples with uncertainty expressions could be a promising approach to mitigate their harmful effects. The findings emphasize the importance of aligning fine-tuning data with the model's knowledge to enhance performance and avoid unintended consequences related to hallucinations.
How does the paper suggest mitigating the risk of hallucinations caused by fitting unknown examples during fine-tuning?
The paper suggests mitigating the risk of hallucinations caused by fitting unknown examples during fine-tuning by using early stopping to avoid overfitting. The study shows that fitting unknown examples leads to performance degradation, especially in later training stages, which can result in hallucinations. By stopping the training early, before the model completely fits the unknown examples, the risk of hallucinations can be minimized. Additionally, filtering out the unknown examples from the fine-tuning dataset is also proposed as a method to reduce the risk of overfitting without sacrificing performance. The paper demonstrates that removing unknown examples has a neutral effect on performance in the early stages of training, but can be harmful in later stages, indicating that these examples contribute to overfitting. Therefore, early stopping and filtering out unknown examples are practical strategies to mitigate the risk of hallucinations during fine-tuning.